So this is a talk that kind of complements the one that Eric Torborg gave earlier, which I just love. It's a talk, kind of a big picture review of modularity and what we've been dealing with in our business, but also, how other industries, even other disciplines outside the tech industry think about this question. I picked pictures of buildings and other structures as motivation. See if this works. Yeah, so I'll start with a little history. We sort of take modularity for granted, but it's actually like everything. It had to be invented at some point. Kind of define what it is and how other people, especially outside of our world, have thought about this concept of modularity, and then drill into software, what's worked, what hasn't, what we still need to do, and then some things that I think are working. So let's start with a little history. So some of the early attempts to create the idea of interchangeable parts, which is something that we sort of think about sort of implicitly when we think about modularity in architectures, is in the 1760s, the French general Jean-Baptiste Becquet, completely botching this, I won't even try, came up with the idea of standardizing cannon bores and shells. We think about this now that if you buy a gun, which we do a lot in the US, you have to buy the right bullets for it and so forth. Eli Whitney, who was an American inventor and is best known for inventing the cotton gin, did sort of the same thing for muskets in the early 1800s, although actually that turned out not to be very successful for some reason, but it was still kind of indicative of it. And I believe it was actually in the American Civil War when it was the idea of standardizing clothing sizes for uniforms was first done. Before that, everything was just handmade to fit. We all kind of know this. This became a big motivation also for software in the 80s and 90s, and that is the idea that electronics can be decomposed into reusable parts and then composed in machines like PCs. Does this work? Well, one of the reasons it actually has worked so well is because of the interfaces we've been able to standardize, and that is typically like buses that are binary lines, but if you add 2 to the n together, you can represent almost anything that you need to represent. So this has proven to be enormously beneficial. And in fact, a lot of these sort of examples of modularity and plenty of others have been studied in the business world. And these are 2 of my favorite books that look at this topic. Actually, both of them are from Harvard Business School professors. Design Rules is a really interesting book that explores modularity in a wide variety of industries, including software. And I'll come back to a little bit about what they said as we get into the definition of things. And you may have heard of the innovator's dilemma as just even sort of a meme, if you will, in the business world of how, for example, someone like Microsoft, a startup, could take on and beat IBM, an established incumbent. And a lot of it was being able to leverage this sort of standards that people invent and then iterate and innovate around those standards. And then one global pattern that you see in a wide variety of cases that I think is very interesting is a pattern of 2 forces in opposition that have a constructive and creative benefit. This book on modularity is actually a collection of papers on modularity in biological systems and evolution and natural language. And then one particular chapter discusses how DNA and RNA really want to be an energy stable configuration. This is actually generally true for all physical systems. They just tend towards the lowest stable energy state that they can. And in this case, it actually resists mutation. But of course, we wouldn't be here today if it wasn't for mutation. So there's still, something happens to excite an RNA molecule that triggers a mutation, and sometimes that's beneficial. And then we get, this sort of life that we have on this planet today. And when I was thinking about that example, I thought about this one in reinforcement learning. So reinforcement learning is one branch of machine learning that was kind of somewhat obscure, even though around for decades, until about 5, 6 years ago, when Google's DeepMind group demonstrated how you could use this technique to learn how to play games and actually beat the world's best Go player, play Atari games, and so forth. And it's, without going into a lot of detail, it's basically teaching a system to navigate in an environment and maximize its reward. And it's once again this sort of contrasting forces of, I need to exploit what paths through the system seem to provide reward, but at the same time, I could be missing even better paths. So I have to have some way of balancing exploitation versus exploration. And it also then occurred to me that this is kind of also the same idea in the open-closed principle that Bertrand Meyer came up with as one of the sort of general principles of object-oriented design, but I think it's true of any modular system, that ideally we need to be able to extend the system, usually by maybe adding on to it, but close it for modification because that's where things tend to break. And I do have to rant a little bit about design patterns. I appreciated Eric's rant earlier about how sometimes in the functional world, people have said we don't need modularity or whatever. But I think one of the mistakes a lot of people in the functional programming community made maybe a decade ago was just sort of dismissing the idea of design patterns as this sort of broken object-oriented thing that we don't really need in functional programming because everything that these patterns describe is already part of the functional landscape. But I think that was conflating the idea of patterns with actual instantiations or instances of them, if you want. And certainly it's true that a lot of the object-oriented patterns are implemented very naturally in functional languages and systems. But functional languages have their own. They have monads, monoids, applicatives, and so forth that really are examples of patterns that are reusable, composable, and so forth. So end of rant. All right, so we sort of talked about the history of it, but we haven't actually defined what modularity might mean. So let's try that. And here what I'll do is I'll take the ideas as they're described in this design rules book, and a lot of this stuff is just stuff we already know that we've figured out in software as well, such as a module is a unit whose structural elements are powerfully connected among themselves and relatively weakly connected to elements in other units. And of course, the way we describe this, and Eric even said this earlier, it's cohesion versus coupling. We want good cohesion within our modules, but loose coupling between our modules. Now, the term design rules in their case, these are the fixed decisions, the things that you've decided and now you're going to move on. It could be that we're going to use a little endian encoding in our CPUs. It could be the bus that we use. It could be that we're going to use Kafka as the backplane for our system architecture. Well, these are the kind of design rules that, good or bad, this is what we've decided to do, and that is then the basis upon which we build everything else. And they define architectures, the pieces and how they are wired together, not controversial. And then we have the same idea that they define interfaces as how we talk to each other. And really, in a lot of ways, the art is how we define these interfaces. And the benefits that they elaborate, again, nothing too surprising, is that if we're not wrestling with fundamental decisions all the time, then we can actually build more complex systems layered on top of simpler concepts. It also allows us to work concurrently if we have loose coupling between modules. And this is, I think, a case where we're embracing as a good idea Conway's law. Conway's law, which was written down by Mel Conway in a paper in the 60s, was sort of a negative observation that if you looked at the architecture of systems, they tended to reflect the organizational structure that shipped them. And he was observing how IBM worked. Conway is still around, actually. I follow him on Twitter. He's a really, really interesting guy. But now we've kind of come to realize, you know what, maybe that's not such a bad idea. If we structure organization to best fit the way we build things, that eliminates the communication among people to a minimum and allows us to work in autonomous units in a concurrent way. So maybe it's not such a bad idea. It also allows us to accommodate uncertainty, namely that we have the flexibility to evolve internally. We can improve the performance, we can improve the implementation, we can fix bugs without necessarily affecting how the system is used and how other people have to use it. And there's some things they didn't really mention in the book that become important benefits for modularity for us in sort of a DevOps perspective, which is that often we need to be able to independently scale modules. This is kind of getting into the subject of microservices a bit, which I'll touch on a little later in more detail. But we need that kind of independent scalability or deployment in general. and the ability to swap out components with better implementations or more appropriate implementations. I wanted to talk about one insight from this book on sort of the natural world in modularity. Now, they talked about a couple of different kinds, one of which we're very familiar with, which is structural modularity. It's the one that we talk about the most in software, but they also talk a lot about procedural modularity and how like a workflow in sort of the biological sense can be structural and plugged together as well. And I think this is an area where we really should spend more time making this a first-class concept in software. And we really haven't done as good a job as we could. And the word procedure is actually a term we've used for decades in software. And here I'm really talking about just the general idea of some sequence of things that we want to do. And in a lot of ways, I've thought about this for a long time. And one of the things that I think has worked really well, just historically, is that when we write like a use case or a scenario or a story or whatever you want to call these things we're writing, a lot of times we like to have a library of reusable components that have good performance or flexible composition abilities. And then we want to glue them together with some sort of scripts. And to basically plug and play as needed. And I thought about the situation with the Python language. Almost everything that people are using Python for these days is a combination of C and C++ code and Python for scripting. Python is I'm actually living in the Python world these days, for better or worse. But the reason it's popular is because it's a simple language, and a lot of people like data scientists don't want to think about all the cool language stuff that we like in Scala. They just want to get stuff done, but Python as a language is horrible for performance. It's even single-threaded in the interpreter. But if you're calling C++ code and something like the hood, then you can get the performance you need while hiding all that complexity from people. So this is, I think, a universal principle. But I think we could do even better. And the question that comes to mind is, well, how would you type a procedure? And I think actually we've seen some hints of how this really ought to be done already today. I'm thinking of Julian's talk about monocle and things like that, where and often just generally in the way we use like for comprehensions and monads is sequentially defining a sequence of steps. I think there's a lot we could do to actually make this more of a first-class idea in our systems, so that and in fact, if we do this, I think it would actually help take us away from cargo culting the idea of reusable libraries and getting everything perfect and then obsessing over stuff, when all we really should be thinking about is, how do I get stuff done? How do I deliver value for people so that they're not just spinning their wheels? And a lot of it is, I need to do this procedure in that generic sense. And how can that be expressed in the simplest possible way? All right, let's drill into software a little bit. I picked what I thought was a representative picture of what a lot of software architectures really look like, if we're being honest. This is a miner's cabin in the state of Nevada, actually. So let's talk about some examples. What about microservices? That's sort of the hot topic. We all kind of have to live this, whether we like it or not. What about DLL hell? This is the term that I used all the time. Those of us who are gray used this all the time in the 80s and 90s to complain about Microsoft apps that would crash when I had the wrong version of some dynamically linked library on my Windows box. But it's not, we can pick on Microsoft all we want, but of course every system seems to have the same problem, jar hell or whatever. What about the failures of OOP? Why did object-oriented programming not live up to its promises? What else might we be using instead? And some interesting things of where I think we're actually figuring out in very pragmatic ways how to modularize certain things that used to be part of monoliths, and how can we learn from those lessons? All right, microservices. David Hannemeyer Hansen went on a rant recently, actually this a couple of years ago, I think now, about microservices. A lot of people, of course, cargo culted the idea that they should break everything into these tiny little things. They had a huge wad of stuff running that they really had no idea how to manage. And sometimes the performance was terrible, making all these like HTTP hops for RESTful services. So it's not a perfect solution, but it does have some benefits. One is actually this Conway's law idea that it helps us break down a very large system into teams in some sense. and minimize the communication required between teams and allow them to work independently in parallel. Deploying microservices has some DevOps benefits, like the ability to scale them independently depending on the need, to rapidly replace some of them if they're evolving improvements in the algorithms or whatever. So there are some benefits if we use them wisely, but they can be, like anything, overused. I think an interesting example, though, of people who kind of maybe drank the Kool-Aid a little bit and then backed off is the Istio project. This is something that's very popular in the Kubernetes world. It's a system basically for managing the connections between your pods as they're running in your Kubernetes cluster. And the way this thing was originally deployed is you would deploy a whole bunch of microservices that were just running the Istio capabilities, let's call them. But they actually abandoned that idea. And the reason is that they discovered that almost all deployments of Kubernetes and Istio in particular were managed by one person. And it was actually a burden for that person to have a whole services to run. So they actually now release everything as just a single service instead of having it all glommed together, as a bunch of microservices. All right, let's talk about this DLL hell concept for a second. This is in Diego, actually. It's a little restaurant. Every system seems to have this problem, whether, it's Python has it, Java has it, the JVM in general. All systems seem to have a problem with versioning libraries. And it wouldn't be so bad if we never changed anything, but of course we do. And getting the versions compatible has always been a challenge. And one of the ways we've tried to address this is really a Band-Aid, which is, well, what if we tried to be honest and just use semantic versioning to really indicate what's going on? But in fact, there's no enforcement mechanism. There's no way to really guarantee that, my version point is actually backwards compatible with the X-1 and so forth. So can we go? I really think this is a problem we have to solve, and we just haven't done it well enough in our industry. Well, here's some things that people have done to try to address this. There's sort of a philosophy in the Clojure community that, if you release something, a type, a function, whatever, you just never change it. You just create a new version if you have to, but the old version is always there. So no one ever has to upgrade anything that they are already relying on. I think that's a very interesting, if extreme, idea, but it may be a more rigorous and flexible way to do it is, could we rigorously define interfaces so that they never actually, we never actually break anything, even if we change the implementation, because it's a two-way contract between the user and the supplier. We'll come back to that in just a few minutes. I think another really great idea is the Unison language and what it's doing. This is the project of Paul Chisano and Runar Bjornason, where they really ask a fundamental question: why do we rely on names to define a connection, to be a connection point? Because maybe that's not the best choice. What if I want to rename something and now I've broken everyone's code that used it, even though functional behavior has not changed, and so forth. So in fact, what they do is, even though you work with names because you're a human and you have to have names, everything is actually linked up using just hash codes. So you can rename a function, it won't break anybody's code. You can use new implementations, different hash or whatever. And I think it's a really good model. The link here is a good, actually very recent blog post that discusses this philosophy. So I'm really looking forward to what this language is doing in terms of innovating, and I hope it's successful, but even if it's not successful, I hope it influences the rest of us. All right, let's talk a little bit about OOP and why that failed. This is a Frank Lloyd Wright interior in Chicago. So why didn't we get the modularity and reuse that we were promised in object-oriented programming? I remember very distinctly, being an old guy back in the 80s, that people were talking about software integrated circuits. They saw what was going on in the little integrated circuits world. We looked at that briefly a while ago. Why can't we do software? Why can't we deliver on that promise? Why didn't we? Well, what we realize now is that inheritance is too fragile. It's a form of strong coupling, but it's completely open-ended. It doesn't really give us any sort of constraints. The other thing that people complained about, who were like old school procedural programmers using C and so forth in the days when OO was taking off, was I've lost track of what's actually going on. I can't sequentially walk through the code as easily anymore. Now, we could do it with debuggers or whatnot, but we really don't have any visibility in a typical object-oriented design of the sequence of stuff. And this kind of goes back to what I was saying about procedures, that maybe we should think more about what are the procedural steps I'm walking through and get rid of all the other ceremony about, maybe obsessing about structure more than we need to. But also, I think it's the lack of constraints was actually the biggest problem. And this is really an interesting idea that's another duality thing, like don't constraints limit what I can do? Don't they kind of prevent me from having the flexibility I need? But maybe that's not actually the case. Let's explore constraints a little bit. And this is an idea that's gotten a lot of currency lately as a tool for actually allowing us to innovate, but not get, wrapped around the axle, if you will, or not getting, completely bollocksed with trying to sort out basic details. So for example, Runar again did this really great talk at Scala World 5 years ago that I bet almost everybody on this video has seen, called Constraints Liberate and Liberties Constrain. And it's the idea that appropriately chosen constraints actually make it much easier to innovate and avoid getting bogged down. So for example, he has this statement, which sounds very cryptic, but we'll see an example in a second, that the more kinds of things something could potentially be, the less we can actually reason about what it actually is. And reasoning becomes a key thing here. The more we can reason about something, the more likely it is we'll get it right. So to see an example, take this particular function signature where, foo, poorly named, but anyway, it takes an array of integers and it returns an int. So what could this actually do? If I had to reason based on the signature about all possible reasonable implementations, what could this be? Well, in this case, I could be returning the size. I could be returning the mean of the values, or, rounded to another integer, standard deviation, there's just, there's a lot of possible implementations. If I wanted to adopt the closure idea that I'm going to define this once and never ever change it, this is a poorly defined function signature because it could be a lot of things. But what if we did this? If we actually expanded it, if we relaxed the idea that it's an integer, but instead said it's some arbitrary type A, this actually gives us it removes the ability to say, well, this is a mean calculation or standard deviation or something like that. We can no longer say that because we don't know what A is. We don't know if A even has that idea. And really, we're actually limited now to only being the length of the array. It's really the only reasonable choice for this particular function. So that actually, by expanding this definition just a little bit, we've actually made it much more precise about the analysis we can do of this function. And this is called parametric reasoning or parametric polymorphism. And it's a really powerful idea for helping us to have one and only possible definition for this function. I forget what's happening next here. Here we go. Let's talk a little bit about side effects. I've done this talk for a general audience, so this is all, I'm preaching to the choir with this slide, but just to be clear about how they undermine our goals. They really make it impossible to reuse things with side effects because we have to carry the whole context. All that stuff that's implicit in when we're doing side effects has to be carried along, which usually means, the more we bring along, the less reusable something is. It's very difficult to compose things because we don't know how side effects will interact when we compose, effectively making it impossible. Concurrency is, of course, the main problem. This is how I got interested in functional programming originally, was thinking about how do we do concurrency in a more sensible and less painful way. And then this idea of reasoning that we just walked through, we really can't do that with side effects involved. It just breaks everything. All right, let's talk a little bit about a few interesting success stories of where I think we've found good ways to accomplish modularity objectives in recent software history. And this will be the last bit. Then is something that happened about a decade ago, which was decomposition of databases as exemplified by Hadoop to give us greater flexibility, but with some trade-offs as well. So this is a schematic diagram of what a Hadoop architecture looks like. Now, if you have painful memories of Hadoop, I apologize. I should have said trigger warning before this slide, I suppose. But anyway, the basic idea was you had some sort of resource manager. You had a distributed set of nodes with node managers and a bunch of hard drives that were managed in a file called HDFS. The illusion of one file system, but actually distributed. And then you wrote your applications that would work with this data in something like MapReduce or Apache Spark or whatever. Well, it occurred to me one day that we've actually deconstructed a database with this model and made it more flexible to plug and play these different components as needed. Sorry about the siren outside. So the SQL part of a database is represented on the left with these MapReduce and Spark jobs. And now we have a little bit more flexibility about how we work with the data. We're not just limited to SQL, although interestingly enough, there are SQL implementations on the left. We can manage resources in Apache Arrow, which is actually pretty broken, and replace it with something like Kubernetes or maybe something even lighter weight. And then we can actually store the data in any format we want, so that we can structure the data in a way that makes the most sense for us and not just what's needed for a SQL engine. So pulling apart these parts as standardized storage, standardized resource management, and most recently Kubernetes is a great example of this kind of standardization. And then developing applications that are decoupled from these particular choices is a very powerful technique for creating very modular, large data systems, and also with a lot of cost savings. Now, there are some disadvantages when you have a database. If they've done their job well, everything is nicely integrated. You just know it's going to work. Some databases accepted, which I won't name. And so there's just a lot of stuff you don't have to worry about. Here, you're taking on more responsibility, so it is a trade-off. The system I'm involved in now is something called Ray that emerged out of Berkeley, and it was basically a reaction to the problems in reinforcement learning in particular we're running into, where they had very flexible requirements, or let's say broad requirements for compute patterns, memory access patterns, for the kinds of different applications they were writing. They needed these things to be highly distributed because they were doing massive compute. Like if you're training a game to beat the world's best Go player, training a reinforcement learning system, that is, you're going to have to run it a lot, with this simulator that simulates Go, with the agent that's trying to learn how to play Go. You just want to run that in parallel a lot in order to actually train it. And so they created this system, Ray, that really, I think what I liked about it, and the reason I joined this company was, I thought they struck the right balance of creating a very minimal API for people who didn't want to think about concurrency. They just wanted to be able to make it happen, and sort of the 90% compromise implementation was good enough for them. They didn't need low-level controls. And in particular, let me mention how I think this benefits the service issues that we've talked about a little bit. So, we already talked about why you might do microservices or maybe not do them. The typical thing in deployment, though, is when you need to scale, what do? You end up standing up a lot of instances of each of them. And you do this for several reasons. One, an individual machine has limited resources, so you're going to have to go to other machines if you're really scaling at a large scale. And of course, you might have a machine crash, so you'd like to be running elsewhere in the cluster for resilience. So this stuff is part of the management burden that has triggered some of the reaction against microservices. To my mind, it's kind of stupid that we have to worry about all of these things. A lot of times, the stuff that's going on to, do the deployments, do the communication, it's all kind of the sort of thing we can standardize. And in fact, a lot of what Kubernetes is doing is standardizing some aspects of this problem. Well, the nice thing about Ray is that it takes a lower level approach of letting you programmatically specify what needs to be distributed, and then it just does it for you. So you get to go back to this idea that you have really one logical instance of a microservice, and then behind the scenes, Ray is just scheduling your work across the cluster. Now, they use the term actor for stateful classes or objects that are distributed, and task are the stateless functions that are running across a cluster. But these things can be anywhere in the cluster. They can be integrated as needed, and it's just sort of transparently handled for you. So I just worry about this sort of driver program, and then everything magically scales across a cluster. This could be done with Akka actors. In fact, I would love to see the Akka team write a simple API so that people who don't want to learn Akka can just do it. Pick your own favorite system for doing the same sort of. In fact, those of you who are working on distributed APIs, think about if you had to teach a Python programmer the minimal amount of Scala in order to use your system, what would that look like for their users? How could you make the 90% case where the good defaults are good enough? How could you make that as trivially easy to implement as possible? That's the sort of thing I think Ray is doing. And the company that I work for is called Anyscale, that is developing Ray. It was spun out of Berkeley. I think this is the last example, and that is Apache Arrow. It basically this was a project where they realized, everyone is coming up with their own way of storing data and managing schema in memory. Spark does it, MapReduce had ad hoc ways. Why don't we standardize this so that everybody can just have one library, cross any kind of application? If you've got a lot of structured memory or data to store in memory, just use Arrow and be done with it. So I love this project for that reason, that it solves a particular problem in a modular and standardized way. Okay, that's it. I appreciate your time, and I guess we'll go on to the next step, whatever that is.